Good morning, good afternoon, good evening, good night. I hope this message or this video rather finds you well. We're going to go ahead and look at topics 4.1, 2, and 3. First thing we're going to look at is inverse functions. So inverse function, when you're given a relation, is just switching x and y values. And so if you look here, if I give you a function 1, 3, 2, 3, the inverse of this set of ordered pairs is going to be 3, 1, 3, 2, right? So we're also going to look at something called a one-to-one. A function is a one-to-one if it passes the horizontal line test. So remember, when we did functions, we did a vertical line test, and if we had more than one x, then it was not a function. If you flip it and you don't pass the horizontal line test, it is not a one-to-one. All right, so let's look at some examples. The first one says to determine whether the function is a one-to-one. So looking here, we're looking at values, the y values to see if they repeat. So here we have 4, 3, 4. For the first one, we're going to say that it is not a one-to-one because the 4 repeats. For the next one, letter B, we have 4, -1, 0. We're going to say that this one is a one-to-one because the y value does not repeat. So don't get the function and one-to-one mixed up. Function is the x's and one-to-one are the y's. So here's an example to try. You can pause the video. You have 4, -5, 6, 1, 2, 4, 0, -3. That is a one-to-one. And then here we have 0, 1, 0, 3, 0, 4, -5. And here you can see that the 0 repeats. So we're going to say that this one is not a one-to-one. All right, so how do we use the horizontal line test? Just like the vertical line test. So for the first one, we can see that when we do the horizontal line test, it goes through more than one point. So it goes through here, here, and here. So because of that, we can say that the graph does not define y as a one-to-one function of x because the horizontal line intersects the function in more than one point. If we look at the second example, we have drawn a horizontal line. We can say that this graph does define y as a one-to-one function because no horizontal line intersects the graph at more than one point. For this next one's kind of tricky. So you can do the horizontal line test and it would pass, but because this is not a function, we can't say it's a one-to-one. So for this one is a little tricky. It says the relation does not define y as a function of x because it fails a vertical line test. If the relation is not a function, then it cannot be a one-to-one. All right, so let's try a few. Again, pause the video. This first one, you're going to say no because when you do the horizontal line test, if I draw a line through here, it goes through more than one point. For B, we're going to also say no because when we do the vertical line test, we know that this is not a function. So we do this, not a function. And then for the last one, we're going to say yes, it passes the vertical and horizontal line test. All right, so next thing we're going to do is determine whether two functions are inverses. We do have a little bit of background information to help us. So one way that we can identify if two functions are inverses is to do composition. So we can do f of g of x and g of f of x to determine if there are inverses. The way that we do that is when we do the composition, we end up with x for both of the functions. So let's look at an example to determine whether the two functions are inverses. So for the first one, we have f of x equals 100 plus 12x, and g of x equals x minus 100 divided by 12. So for A, we're going to do g of f of x, and we're going to do f of g of x. So for g of f of x, remember I always tell you to work inside out. So my inside function is 100 plus 12x. We're going to take that and we're going to put it into our g function for x. So we're going to have 100 plus 12x minus 100 divided by 12. And then we're going to simplify, right? So 100 minus 100 cancels. 12 divided by 12 is 1. This leaves us with x. So we're going to do the same thing for f of g of x. So our inside function is x minus 100 divided by 12. We're going to take that and we're going to plug it into our f function because f is on the outside and see if we get x. So we're going to rewrite the f of x function as 100 plus 12 times x, which is my inside function here, x minus 100 divided by 12. And then when we continue to solve, these cancel. I'm left with 100 plus x minus 100. The hundreds cancel, and I'm left with x. So because when I did the composition, f of g of x and g of f of x, they both ended up being x, I can say that these two are inverses. So we can say yes for this one. All right, so pause the video because I'm going to erase so I can do B. So for B, we have h of x equals cube root of x minus 1, and then k of x equals negative 1 plus x cubed. So again, we have to do h of k of x and k of h of x. So inside function, k of x is negative 1 plus x cubed. We're going to take that and plug it into here. So we get the cube root of negative 1 plus x cubed minus 1. So here we end up with the cube root of negative 1 minus 1 is negative 2 plus x cubed. Well, this doesn't equal x, so we can't say that this is an inverse. But let's say you started with k of h of x first. So we can try that. H of x is the cube root of x minus 1. We're going to take that and plug it into this function. So negative 1 plus the cube root of x minus 1 cubed. So just like a square undoes a square root, a cube undoes a cube root. So what you end up with here is negative 1 plus x minus 1. This gives us x minus 2, which still does not prove that these are inverses. So for B, you're going to say no. Right? So identify if A and B are inverses. Pause the video. So for A, you're going to say no. For B, you're going to say yes. Right? Moving on to how to find an inverse. So the steps of finding an inverse is just like when we did the relation and we had 1, 3, and we flipped it and we said 3, 1. You're going to replace f of x with y, interchange the x and y, solve for y, and then replace y with the inverse. So whenever you see f of negative 1, that means inverse. So let's try an example. Here we have, write an equation for the inverse of f of x equals 3x minus 1. First thing I'm going to do is I'm going to rewrite f of x as y equals 3x minus 1. And then my next step is to switch x and y. So x comes here, equals 3y minus 1. Our next step is to solve for y. So I'm going to add 1 to both sides. X plus 1, equals 3y. And then final step is to divide by 3. So we get x plus 1 divided by 3 equals y. So our inverse of x equals x plus 1 divided by 3. Or you can write it as 1/3 x plus 1/3. Both of these are acceptable. Most students just stop here at the first one. All right, so try this next one. We have write the equation of the inverse for f of x equals 4x plus 3. You can pause the video. And your inverse is x minus 3 over 4. All right, so we're jumping to exponential functions. Exponential functions have something called base b. So you have 3 to the x, 1/3 to the x, square root of 2 to the x. You can also write square root of 2 to the x as 2 to the 1/2 raised to the x. So for non-exponential functions, the base is not a constant. The base can't be negative. Here you can't have a base of 1. All right. So we're going to look at graphing these functions. We're going to find equations or points rather that are a little bit easy to solve. And this is going to help us when we go to do the inverse, right? So if I have 2 to the x, I'm going to pick my favorite points. I'm going to write x and y. I'm going to use -2, -1, 0, 1, and 2. So if I am plugging in these x values into my equation, 2 to the -2, we don't like negative exponents, so remember we flip it, so it becomes 1 over 2 squared. So once we move the exponent, it becomes positive, so is 1/4. Or you can say 0.025. And then we're going to try -1, so 2 to the -1 becomes 1 over 2, which is a half. Or we can say 0.5. Then we're going to say 2 to the 0. Anything to the power of 0 is 1. 2 to the first is 2. 2 to the second is 4. And then I'm going to plot these points. So -2 and 0.25, very close to the x-axis. -1.5, that's halfway between 0 and 1. 0 and 1. 1 and 2. 2 and 4. Right, so our graph looks like this. And this is called exponential growth. Right, so you see exponential growth when you're talking about bacteria growth, viruses. I think about when we had COVID and how it was growing rapidly. Sometimes money in accounts grow exponentially, right? So for g of x, we have g of x to the g of x equals 1/2 to the x. So again, we're going to find points. I'm going to use a different color. I'll use blue. And this time we're doing 1/2 to the x. I'm using points, same points, -2, -1, 0, 1, and 2. So when I do 1/2 to the -2, we're distributing that -2 to everything. So 1 to the -2 over 2 to the -2. I don't like these negatives, so I'm going to flip it. 2 squared over 1 squared equals 4 over 1, which is 4. Now let's do -1. So 1/2 to the -1. I have 1 to the -1. Sorry, I wrote 2 over 2 to the -1. Again, we're going to flip it. 2 to the first over 1 to the first is 2 divided by 1, which is just 2. Anything to the power of 0 is 1. 1/2 to the first power is 1/2. Last one is 1/2 to the second. That becomes 1 squared over 2 squared, which is just 1/4. And just like the previous ones, we can change this to 0.5 and 0.25. All right, so let's go ahead and plot these points. And so for -2, we're at +4. -1, we're at 2. 0, we're at 1. 1, we're at a half. 2, we're at 0.25. And so our graph looks like this. So this is exponential decay. And you can see these type of equations with beach erosion. You can also see it a little bit with medication. So when you're taking something like a pain medication and the medication is wearing off, it's exponentially going down. Okay. All right. So I want you to try these, come up with examples. The numbers are going to be a little big. So try to do for the first one, 5 to the x, you can try 5 to the -3, -2, -1, 0, 1, and 2. And then for the 1/5, you can use the same numbers that we used in the previous example. All right, pause the video. And these are the equations or graphs rather that you should have gotten. Exponential growth when the number is greater than 1. Exponential decay when it is between 0 and 1. All right, so let's look at some interest or simple interest problems. So here it says, suppose that $P in principal is invested or borrowed at an annual rate for T years. Then we have these equations that I will give you on assessments. So we have simple interest. I'll give you what some of these letters mean. So the I here is interest. P is the principal or your starting amount. Here for this one, and T is time. So that's for the first one. The second one, that A just stands for amount. The P is still principal. The R here is rate. Your rate as a decimal. N is the number of times compounded. And I'll talk a little bit more about that when we get to that compounded question. The last one is for compounded continuous or being compounded continuously. So A is still amount, P is still your principal. Base E is, and we're going to talk a little bit about it when we talk about natural log, but it is a number kind of like pi. R is your rate, T is your time. All right. So again, I'll give you these formulas for assessments and on your final exam. So let's look a little bit more into compound and continuous compounding. So it's suppose that $5,000 is invested and pays 6.5% per year under the following compounding conditions. So the first thing you're going to want to do whenever you see these type of equations is change the percentage to a decimal. So one way to remember this is you always move the decimal to the left, 1, 2, and then that will tell you where the decimal will land, and you're at 0.065 as a decimal. So 6.5% is 0.065 as a decimal. So let's look at our equation. So what you need to remember is that when you're talking about annually and you're talking about compound interest, you're looking at this formula right here. Annually, this N right here is going to be 1. Quarterly is 4. Monthly is 12. Daily is 365. And for E, the last one, compounded continuously, you're going to use this formula right here. So here they tell us determine the amount in the determine the total amount in the account after 10 years with each option. So I went ahead and kind of showed you what you needed to do. So here the end value is 1. My principal amount, that's how much I invested, 5,000. 1 is always in the formula. My rate is 0.065. You can either put the 0 in the front, but you don't have to. It's the same thing. N is 1. time, and then here you're doing 1 times the time. So 1 is the number of times compounded, and then in this case, we're talking about 10 years. So right here. All right, so when you plug this in a calculator, you're gonna get 9,385.69. I'll show you how it looks when you plug it in Desmos. Um, and then you can kind of use that to help you if you don't have your own graphing calculator. All right, so let me go ahead and show you what it looks like in Desmos. So we're putting in the formula for being compounded 1 time. So I'm putting in 5,000, 1, sorry, plus, and then in parentheses, I'm going to do the rate, which is 0.065 divided by the number of times that's compounded, which is 1. Close the parentheses, and then my exponent is going to be 1 times 10. You can just put in 1 times 10 if you want, or just put in 10 because you know what 1 times 10 is. Up to you. And notice you have $9,385.68.68. So be careful because if you don't round correctly, it's going to mark you wrong. So remember, if it's 687, this is going to round up to 69.69. All right. All right, so let's look at what happens when we do quarterly. Quarterly, you're putting in the number 4 for N. And when you plug in, you get $9,527.79. Monthly, you're putting in 12. Daily, you're putting in 365. And for continuously, you're not using this formula. You're using this formula here. Continuously means it's happening all the time. So you're plugging in 5,000 base E, same values here for the rate and the time. And again, I'm going to show you how to plug that into Desmos. So your principal is 5,000. Base E, you can just hit the E. Raised to the rate, which is 0.065 times your time, which is 10. Again, be careful with rounding. And then when we go back here, you can see the 9,577 and 70 cents. All right, so go ahead and try to plug in. This time you are using a rate of 4.5%. You're investing $8,000 and they want you to determine the amount in the account after 5 years. So I'll do the first one with you. And then we will look at the others. I'll give you the answers for the others. So for the first thing I'm going to do is I'm going to change 4.5. I'm moving the decimal twice. So this is equal to 0.045%. I'm sorry, or decimal rather. And then when we plug in chug, we have our base amount or principal amount, which is $8,000. 1 plus your rate divided by the time annually is 1. And you're raising that to the 1 times 5. So when you plug that into Desmos, you get $9,969.46. So for the others, you're changing this one and this one based on information. So for quarterly, you're changing it to a 4. Monthly, you're changing it to a 12. And daily, you're changing to 365. Compounding continuously, you're using the base E, and you get $10,018.58. You can also use your exponential function and other applications. So it says the half-life of radium is 226. Radium 226 is 1,620 years. In a sample originally having 1 gram of radium 226, the amount in grams of radium 226 presented after T hours is given by this equation. T is the time in years after the start of the experiment. How much radium will be present after 1,620 years, 3,240 years, 4,860 years. So for all of these, you're just taking the amount. And so here we're going to do A of 1620. And we're going to plug it into our formula. 1/2 to the 1620 divided by 1620. And get our answer. We're going to plug that into Desmos. So 1/2 raised to the 1620 divided by 1620. So you get 0.5 or you get 1/2. And you can see that you're really just dividing by 1 or raised to the first power. So our answer for this one, you can write it as a decimal or as a fraction. For B, we're going to do the same thing. We're going to do A of 3,240. So we're doing 1/2 to the 3,000, sorry, because T is 3,240 divided by 1620. And again, I'm going to go into Desmos and change my top number to 3,240, and I get 0.25. All right, so 0.25. And then one more. This time we're doing 4,860. Plugging it into the formula. Divided by 1620. And going back to Desmos. Changing the top number to 4,860. And I get 0.125. So this could also be 0.5. This could also be 1/4. And this could also be 1/8. Let me move this out the way. This is an 8. All right. Go ahead and try this next example. I give you cesium-137. It's a radioactive metal. It has a short half-life of 30 years. And they give you a sample that has an original gram of cesium-137, original 2 grams. The amount AFT in grams of cesium-137 present after T years is given by AFT equals 2 times 1/2 T to the 30th. So they want to figure out how much cesium will be present after 30 years, 60 years, 90 years. Pause the video, plug the numbers in, and see if they match my answers. All right, so check. Then we're going to move on to the next thing. Next thing is logarithmic functions. So logarithmic functions are inverses of exponentials. So when you graph a exponential function, we looked at them. They kind of look like either like this, where you have exponential growth, or like this if you have exponential decay. Logarithms do the kind of look like the flip of that. So either you're going to have a graph that looks like this. Sometimes they look like this. Okay. So we're going to look at that in a minute. But whenever you have a logarithm, it looks something like this: log base b of x. B is the base, x is the exponent, y is, I'm sorry, x is the value. So you can interchangeably write these, and we're going to look at examples of that. So it says, write each equation in exponential form. So if I'm looking at the first example, I can say 2 to the 4th power equals 16. So notice that this is the base, this is the exponent, this is what it's equal to. The next one I can say 10 to the negative 2 equals 1 over 100. And for the last one, I can say 7 to the power of 0 equals 1. So go ahead and try to do these three examples. All you're doing is writing it in exponential form. Pause the video. These should be your answers. You can also go backwards. So if they're asking you to write it in logarithmic form, they give you an exponential. You're going to have log. Let me do it down here. So you're going to have log, the base is 3 of 81 equals 4. For B, you can write it one of two ways. So a common log is going to have a base of 10. So for example, if you see log of 5, this is really log base 10 of 5. So you can write this as log base 10 of 1,000,000 equals 6. Or you can just write log of 1,000,000 equals 6. And then for the last one, for C, you're going to say log base 1/5 of 5 equals -1. All right, so try to write these next few. Pause the video. These are your answers. So now we're moving on to actually evaluating these. So the best way to kind of think about these is this is asking me 4 for A, 4 to what power equals 16, right? So we need to figure out what goes on this other side. So my answer here, if I say 4 to the second, 4 to the second power is going to give me 16. My answer for A is 2. B, 2 to what power equals 8? Well, I know 2 times 2 is 4. 4 times 2 is 8. So I know I need 3 2's to get to 8. So my answer here is 3. For C, we got to do a little bit of work because we have a fraction, right? So we're saying 1/2 to what power gives me 8? Well, if I'm looking at this fraction and if I put in a 3, right? So 1/2 to the third power, that's going to give me 1 to the third over 2 to the third, which equals 1/8. But I need this to be a whole number. So what I can do is I can make this negative. So 1/2 to the -3 gives me 1 to the -3 over 2 to the -3. We don't like these negative fractions. We got to flip it. 2 to the third over 1 to the third gives me 8 over 1. So that's what I'm looking for. So I need a negative here. So whenever you're going from a fraction to a whole number, keep in mind that it's going to be a negative value. So my answer here is -3. All right, so log base 5 of 125, evaluate log base 3 of 81, and log base 4 of 164, of 1 over 64. You can pause the video. These are our answers. All right, so the next type of log, we have two different types. We have a common log. Remember, I said a common log has a base of 10. And then a natural log is another type of log. So common logs undo exponentials, or they're the inverse of exponentials. And natural logs are the inverse of base E, which is what we saw when we were doing the interest problems. So here there is a shortcut. So this is saying 10 for A. 10 to what power is going to give me 100,000? Well, if you look at the number of zeros we have here, that's going to be your answer. So here I have 5 zeros. So 10 to the 5th power is going to give me 100,000. So my answer for this first one is 5. This next one, you got to think of it as I had a decimal here and I moved it to the left 3 times. Whenever you move to the left is negative. So my answer for this is -3. So you always move it behind the first number greater than 0. So remember in the beginning of this, I said that natural log and base e undo each other, or they're inverses. So if I have natural log times base e to the 4th, these two cancel each other out, and it leaves me with just a 4. D is a special case. If you have natural log times 1 over e, I can rewrite 1 over e as e to the -1, right? Because e to the -1, we know we don't like that negative in the exponent, so we could write it as 1 over e when we move it down, e to the first. So because of that, this is similar to C. I see that I have natural log and e. That cancels out. My answer is -1. All right, try these. Log base 10 of 10 million, log base 10 of negative, 0.1, natural log of e to the 5th, natural log of e. So remember I said count the zeros for this one. You move left 1 here, ln and e cancel, ln and e cancel here, and we're left with 1. All right, moving on to basic logarithms and their properties. We're going to do a little bit more with logs as we move through this unit. So these are properties, just kind of get them down. It's a lot easier to understand them when we actually are doing a problem. So if I have this here, I'm going to explain it and then I'll go through some of the others. So this is saying a log base 3 of 3 to the 10th power, right? So this is really just saying 3 to what power is going to give me 3 to the 10th? Well, if we want these two to be equivalent, our answer is going to be 10, right? But there's a shorter way to do this. I can see that I have log base 3 of 3, which really kind of cancels itself out, and it just leaves me with 10, right? Natural log of e, we know that that's 2, so my answer for A is 10. My answer for B is 2. Log base 11 of 11. Again, 11 to what power is going to give me 11? 1. Log base 10 of 10, also 1. Log base square root of 7 is of 1. So be careful with this. I know it looks crazy because you see a square root. So this again is asking you square root of 7 to what power equals 1. So remember, anything to the power of 0 is equal to 1. So my answer here is 0. Natural log of 1. So remember, you can raise this to the e, right? And so this gives me 1 here. Log base 5 of 5 raised to log base 5 of c squared plus 4. This cancels. I'm left with this. And same thing for h. I am left with this because 10 to the log base 10 cancels out. All right. So again, try a few of these. Pause the video, see how you do. All right. Come with questions next class if you have them. Okay, so we are moving on to graphing logarithmic functions. So I've been saying that says logarithmic functions. I'm just going to move it out the way because of the graphing. So it says graph the function log base 2 to the x and log base 1/4 of x. So remember, because we know about inverses, we know that we can switch the x and y. So if I wanted to graph a log base 2 to the x, I can find the values of 2 to the x and then flip them. So my value for A is going to be 0.25, -2, 0.5, -1. 1, 0, 2, 1, and 4, 2. Ran out of space. And so I can plot these points. I'm going to plot them over here. 0.25 is here, and -2 is here. Oop, a little too big. Let's make it a little bit smaller. And then 0.5 and -1, that's about here. And 1 and 0, 2 and 1, 4 and 2. So if I connect my points, my graph kind of looks like it's going up like this. And there is my graph. So we're going to do the same thing with log base 1/4 of x. I'm going to plot these and then I'm going to switch them. So I don't have 16 and -2, but that will be out here somewhere. So like down here. And then I can do 4 and -1, 1 and 0. I'm sorry. Yeah, 1 and 0. And then 0.25 and 1. And then 0.6, 0.06 and 2. So this graph is kind of coming down like this. It's not on the other side of 0. It's coming down kind of close to 0. And it's doing this. All right. So again, try these. Remember here you're plotting 4 to the x first and 1/2 to the x and then switching them. All right, so these are your graphs. So just like exponential functions, if you have a base that's greater than 1, it's increasing. A base that's a fraction, it is decreasing. All right. So that's it for 4.1 to 4.3. Please come with your questions. And I'll see you next class. Have an amazing weekend. Take care and be safe.